Welcome to the Motion Graphs Explained video. This is part 2. If you are skipping part 1 and going to part 2, please listen to the first few seconds of part 1 to hear everything I had to say about how to take these notes. All right, part 2. This is the second page. These are snapshots of constant acceleration. So we will have changing velocity. In the last page or the last part of these notes, Part 1 was all about constant velocity, where objects were not accelerating. In this example, this entire page has objects that are accelerating. They are speeding up or they are slowing down, depending on their velocity and acceleration signs. Now, just to review, when velocity is positive and acceleration is also positive, the object will be speeding up. The same is said for when the velocity is negative and the acceleration is negative. When both of them have the same sign, they will be speeding up. But the opposite is true for velocity and acceleration with opposite signs. If velocity is positive and acceleration is negative, that object will slow down. Or if the velocity is negative and the acceleration is positive, that object will also slow down. Let's take a look at these graphs now. First, we have displacement versus time, velocity versus time, and now a new graph, acceleration versus time. Again, please remember, displacement can be called position or distance or displacement. Just get used to the different words that they are used to describe. These are all T graphs because we're talking about negative and positive velocities, displacement, and accelerations. So let's just jump right into the examples. Our first one is pink and it says constant, medium, positive, acceleration, aka speeding up. Now, if my velocity and my acceleration are both positive, this is the graph I'm going to have. This object probably started from rest and then was given a positive acceleration. But if something is accelerating positively, that means its velocity is changing in the positive direction. It's getting faster and faster and faster. One way we can see this is if we were to draw a tangent line, and I'm sorry that I don't have something that I can actually do a drawing with, but if we were to draw a tangent line, which means like a straight diagonal line that is perpendicular to the curve right here, this tangent line would start very flat and get steeper and steeper and steeper. So as we can see, the curve is getting steeper and steeper as time goes on. So this object must be speeding up. Because this is happening in the positive direction, that means the velocity was probably positive. The acceleration is positive. So if we jump down here to the velocity graph, we're going to see because we started from rest, it starts at 0, 0. We have a positive sloping line, and that means the acceleration was positive. And the velocity is increasing in the positive direction above the x-axis. The same matching graph can be shown right down here. This very faint pink line shows a positive constant acceleration. Now, what's interesting is back on the last page, our displacement graphs were all diagonal linear lines, and our velocity graphs were all horizontal linear lines. Now, when we're looking at these three graphs, notice that it has shifted. Acceleration is now the horizontal linear line, velocity is now the diagonal linear line, and displacement is not linear at all. We have 3 degrees of motion here, and that's why we're starting to see a parabola or a parabolic shape. All right, so this flat acceleration line matches the slope of the velocity graph, and the velocity graph was created by calculating the slopes of the tangent lines of the displacement graph. We will not calculate tangent line slopes, but I just want to let you know where that comes from. Let's take a look at blue. Blue is constant, medium, positive acceleration, but it's slowing down. What that means is its velocity must be the opposite sign. So you guessed it, the velocity was negative. If we have a negative velocity to start, that means that we're going to have a negative sloping tangent line. See how this curve is sloping negatively but it's flattening out. It's getting less steep as time goes on, and eventually it will go nice and flat. So this means that the object is slowing down, okay? If we were to roll a ball down this blue line, the ball would be moving the fastest right here at the top and would actually be slowing down the flatter the line goes. Again, if we were to take the tangent lines, we would then find that the velocity was going from very negative and slowing to a stop. This has a positive slope, meaning the acceleration is positive. It started negatively because it's below the x-axis, but it is approaching the x-axis, meaning it is approaching zero velocity, and zero velocity is when something has stopped. This is slowing down. But take a look down here. The blue line is right below the pink line. Both of these objects, pink and blue, have the exact acceleration. Look at the slopes of these lines. These are parallel lines. They have the exact same acceleration, and they both have positive accelerations. It's just that the pink object started with a zero velocity and went positively, and the blue line started with a negative velocity and went positively. So this one was speeding up, whereas this one was slowing down, even though their accelerations are identical. The last two graphs also have identical accelerations. Let's take a look at those. The orange graph has a constant medium negative acceleration, and it is also slowing down. So if the acceleration was negative, we would need the opposite sign for velocity, which is positive. See how this orange line starts positively? It's moving in the positive direction. And if we were to take the tangent line, we would see that it is steep, but getting less steep, and very flat. So it was moving positively to begin with, but because this acceleration was negative, it's going to slow it down. If my curve is getting flatter and flatter and flatter, that's an indication of slowing down and that my acceleration and velocity are in opposite directions. This orange line matches the velocity graph here. We started with a positive velocity, and if the acceleration is negative, that means our slope will be negative. So our velocity started positively above the x-axis. It had a negative slope as it went towards zero velocity, which is stopping. Again, the acceleration matches this value of the slope. Last but not least, we have the green graph. Constant medium, negative acceleration, but speeding up. The green graph starts as a very flat slope, and the tangent line starts to increase in steepness. So this object is speeding up in the negative direction. Even though it started positively, we could take this green graph and move it to the origin and make it down below. That's fine. But what matters is the direction of the movement. So this object started away from the origin, and it started to go negatively. And its velocity started at rest and was also going negatively because it's moving away from the x-axis. The slope of the green line and the slope of the orange line should be parallel. I don't think I drew them very well, but they are identical because the acceleration is the same for both. The green and the orange lines both have the same negative acceleration, but the green line, it was an object that started from rest and was just accelerating negatively, getting faster and faster in the negative direction for velocity. Again, remember, if the signs are the same, that means they're speeding up. And if the signs are opposite, that means they're slowing down. Here's another couple cheats. To go from a distance versus time graph, we calculate the slope. To go from a velocity versus time graph, we calculate the slope to get to the acceleration time graph. So if I want to go to a distance versus time graph to a velocity graph, I would find the slope. But if I wanted to go backward from a velocity graph to a displacement graph, I would calculate the area. The same can be said for acceleration and velocity graphs. Now, the concavity of a graph. The concavity is the curvature. The curvature or concavity of the displacement versus time graph is how you determine if the acceleration is positive or negative. If it's concaving up, like a bowl, if you could pour something into it, if it's concaving up, that means it's a positive acceleration. And I use this little cheat with the smiley face. It's positive. If it's concaving down, a sad face, that means that the acceleration is negative. So you can have an object moving with a positive velocity, but it's concaving down, showing that that positive velocity is decreasing and getting slower and slower. Or you can have a positive concave with a negative velocity. So this one had a negative velocity, but a positive concavity, showing that this one is also slowing down. So if the concavity is opposite of the sloping of the graph, that also means it's going to slow down. If the concavity is the same, then that means it's going to speed up, which would be the green and the pink. I hope this was helpful, and if you have any more questions, please feel free to come see me.